This video is going to look at conservation of momentum, which we really care about specifically because of collisions. So jumping right into that. Collisions occur when two objects attempt to exist in the same position or the same spot in space at the same time. So for example, you're not colliding with the person who sits in the chair that you sit in a different period because that's a different period. Likewise, you're not colliding with the other students in a classroom because they're in different positions. So even though it's the same time, they're in different positions. Even though you sit in the same desk as someone else, that's at different times. So no collision occurs. But if there was confusion and, two classes met at once, then you might both try to sit in the desk and you would collide. When there's a collision, objects will exert forces on each other because of Newton's third law, right? If they run into each other, if they hit, one object's going to push in one direction, the other object's going to push in the other direction. So they're exerting forces which create an impulse and therefore changes in momentum. I don't know why I started writing a C there. And if we think about it from Newton's third law, we know that those two forces have to be equal and opposite. So I have to have one force this way. We'll call that the negative force of one object and the other force. If they're pushing on each other, they can only push on each other for the same amount of time by definition. So delta t is going to be the same. So in both cases, the change in momentum is equal and opposite. So one object will gain momentum, the other object will lose momentum. I don't really like using those words, but for sake of plus and minus, that kind of makes sense for our initial conversation here. And the net change, though, of the objects in total is 0. And that's this idea of conservation of momentum. So in collisions for isolated systems, momentum is conserved. So if one object has its momentum go up by 10, so it gets plus 10 kilogram meters per second of momentum, the other object has to lose 10 kilogram meters per second of momentum. And that's what we're saying here. A quantity is conserved if the total amount remains constant, or the total amount doesn't change. And a system is isolated if it has no external forces acting on it. External. So the most common of this would be friction. So for example, if two cars hit each other and they're sliding on ice and we assume there's no friction, that would be an isolated system. Whatever momentum one car gains, the other car has lost. And this is known as the law of conservation of momentum. And the way that we write that, there's two ways. The first way is that the total initial momentum equals the total final momentum. In other words, again, the sum of all of the initial momenta equals the sum of all the final momentum. Or you can also write it as net change in momentum equals 0, which can also be written as P minus P naught equals 0. And those should actually be the change in the net momentum. So let me write that a little clearer. Change in net momentum, or change in total momentum. And you can kind of see how these line up, right? If I move this P over, then we have the same thing on both sides. And for this class, we're going to generally assume that all systems are isolated. Unless I specifically tell you or specifically ask, is a system isolated? If it just says, here's a collision, you can assume it's an isolated system. So here's our first example. Two athletes are running towards each other. Athlete A has a mass of 75 kilograms and is running to the right with a speed of 4 meters per second. Athlete B has a mass of 80 kilograms per second and is running to the left with a speed of 3 meters per second. What is the net momentum of this system, meaning both athletes? So we have athlete A here. Mass A is 75. The velocity A initial is 4 meters per second to the right. And then athlete B here. Just going to label all this on. He has a mass of 80 kilograms, or she has a mass of 80 kilograms, and they've got a speed of 3 meters per second to the left. Now, this is a place where, generally speaking, we want to start getting careful. And anytime we have numbers that are pointed in our positive direction, we label them as positive. If they're in the negative direction, we label them as negative. And that'll become clear as we do more problems why that's important and useful. So if we want to find the net momentum, that's just going to equal PA plus PB, which is going to equal MA VA. I guess these don't actually need to be initial and final, but we'll leave them like that. Plus MB V. And it's already solved for our, or it's already isolated, this delta P that we're trying to solve for. So that's going to be 75 kilograms times 4 meters per second plus 80 kilograms times negative 3 meters per second. 75 times 4 should be 300 kilogram meters per second. 80 times 3 is negative 240 kilogram meters per second. So the net momentum of this system is 60 kilogram meters per second. And we can add just to the right so that we know without a doubt that we're thinking to the right. Is this necessary? No, but it kind of helps just make sure we're all on the same page. So this means after they collide, whatever they end up with, whatever their final momenta are, if I add them again together, I should get 60 kilograms to the right. So maybe this athlete A bounces backwards and athlete B also bounces backwards. Well, we know the net result should be to the right. Maybe athlete A pushes athlete B backwards, but they go really slow so that we get this 60 kilogram meters per second to the right. There's all sorts of things that can happen. We don't know what is going to happen. We just know that the total momentum afterwards is going to be this same amount of 60. A 0.75 kilogram basketball is rolling to the left and hits a 0.5 kilogram soccer ball. The soccer ball is initially at rest. After the collision, the basketball continues rolling to the left with a speed of 0.3 meters per second, and the soccer ball rolls to the left with a speed of 1.8 meters per second. How fast was the basketball rolling before the collision? So this is a problem where you really see why it's useful to label and create good diagrams. So I'm going to start with the mass of the basketball. It's equal to 0.75 kilograms. I know it's a little hard to read, so I'll try and write the rest of these better. And then it has some unknown initial velocity that we're trying to solve for. We also have our soccer ball, so mass of the soccer ball equals 0.5 kilograms, and the initial velocity of the soccer ball is 0 meters per second because it's at rest. Now we'll draw after the collision, so we'll just write mass S so that we don't have to relabel it. If you want to relabel it, that's fine. It rolls with a speed of 1.8 meters per second, and the basketball has a final speed of 0.3 meters per second. Now, in this case, because everything's going to the left, I'm just going to call to the left positive and to the right negative. If you don't like that, it's negative, just put a negative on this 1.8 and a negative on this 0.3. You'll solve it, you'll find out you get the exact same results. Actually, you'll get a slightly different result, but it'll just be because you've got this negative, that means your initial velocity will have to end up being negative as well. Okay, so here we've got our picture. So we've got before the collision and we've got after. So now we know that the total momentum before has to equal the total momentum after. So in other words, mass soccer ball, initial velocity of the soccer ball plus mass basketball times initial velocity of the basketball has to equal the mass of the soccer ball times the velocity of the soccer ball plus the mass of the basketball times the velocity of the basketball. We know that this is 0 because the initial velocity is 0. That's a place that it is fine to plug in anything that you know is 0 because it's going to cancel out nicely. Excuse me. Solving for the initial velocity of the basketball, that's going to be MSVS plus MBVB, weird B there, divided by MB. The initial velocity of the basketball is going to be 0.5 kilograms times 1.8 meters per second plus 0.75 kilograms times 0.3 meters per second, all divided by 1.75. And that'll give you a number that I believe this is going to be 0.9. This is going to be 2.1. Yeah, 2.1 plus a little bit. So this number should be about 3. This number should be about 4, I think. 3, 3.5, 4. Something in that ballpark. Double check it with a calculator, but for sake of time on this video, I'm going to cut it off here. If you have questions, let me know. But that, yeah, is a quick kind of rough estimate of around what your number should be.